and I'm going to make the propanoid chloride. So 1, 2, right? So I have 3 carbons there, propanoid, bromide. Okay, and this is bromide. I will put all the lone pairs. I don't promise I will keep writing them. Okay. All right. And what else we have? We have aluminum bromide catalyst. Okay, I'm going to use a different color for this. Okay, aluminum bromide. Okay. So these colors will help us to get some idea. First of all, look at what is over the arrow. So when you look over the arrow, you have Lewis. You have a catalyst, right? That's a catalyst. And that's a Lewis acid or a Lewis base? Acid, okay? So now, and then we have this here that is a carbonyl and it has a bromide, has a leading group here. So just looking at this, what kind of reaction we say this is? It's Friedel, yeah, first of all, give me the name. Friedel, Crafts, acylation. And the reason I would say acylation, I would have to use the color to relate it to. It's called acylation because of that blue structure I wrote, right? That's the acid group, okay? Now, so let's see first of all what I have over the arrow and what it's going to give me, all right? So I'm going to write the mechanism over here. So in the meantime, over here, let's work to see what we have. We have this compound here. I'm just going to write it a little bit differently. Okay. It's just easier. Just write upwards. Okay. And of course, this has lone pairs. Okay. And then here's the bromine. Now the bromine has lone pairs. And now next to that, I will put the aluminum bromide. Okay. We know that there's lone pairs in all the bromides. I'm just going to not do all of them. Just saying this here. So this goes over there. So this green arrow goes there because the aluminum has empty balloons, empty orbitals, there's d orbitals in the third row. And that's what qualifies it to be a good Lewis acid. Acids receive electrons. You see the purple aluminum receives the green arrow, right? It receives the green lone pair. So as a result of this, what we're going to get is this over here. And let's try to squeeze in here, bromine. And then aluminum. The other bromides around it. And what is the bond between the green bromine and the purple aluminum? Green. And by the way, what were the charges over here? 0. The charge is 0, right? We have a package of zeros, like 0 attacking another 0. So whatever the charges are here should be 0, right? What is the formal charge over bromine? Right? Because if you look at the bromine, the periodic table has 7, right? If you count the box, it's 7. So here's 1, 2, 3, 4. He takes one of those 2, 5, and one of those 2, 6. So it's short by 1. So that's a plus 1. And we said the whole thing has to be 0. There must be minus 1 someplace. Where is that minus 1? The aluminum has a minus 1 formal charge. All right? And so now, what happens in the next step, that's a temporary situation, if you may. I mean, just put it in brackets. That's not the resonance brackets. That's just something temporary. And then, of course, this green bond here leaves. And as a result, you're going to get this situation here. You're going to get this, then this, and then it's going to be a plus charge on the where? Carbon, right? Okay, now would you consider this blue thing I wrote as a nucleophile or as electrophile? Electrophile. Now we can answer the question that was said earlier, what kind of reaction is this one here? It's an EAS. It's electrophilic, right? And actually, if I want to be technically correct, I'll put this in blue because the colors help you to see why we call something something, right? Because of the blue thing I've drawn, that's why it's electrophilic, right? Electrophilic, right? Because of the electrophile created, aromatic, right? The substitution, right? So EAS, okay. All right, So electrophilic aromatic substitution. Notice in all this talk, I didn't talk about the Benson ring. One more thing before I go there. Is there anything else missing here? Right. So that's something that most people forget. So you need to put the resonance here. Okay. Okay. What I mean here is, okay. And so the resonance would be, I will take the blue pair and collapse it over here. And as a result, I'm going to have a triple bond now, right? And here's the oxygen, okay? And here is this. And of course, I have 1, 2, 3 carbons. I'm doing this because, of course, I hope you know how many carbons do I have here? 1, 2, 3, right? Many times the computer prints it this way, so you know, I'm saying this verbally, but make sure there's a carbon here, right? And sometimes it's confusing to students, right? So if I have this in an exam, you know, that's how we read it, but just here's 1, 2, 3 carbons. 1, 2, 3, there's a carbon here, okay? Now, is there any, what is the charge here? Plus. There must be a plus here. Where is that plus sitting now? For the oxygen, right? And how do we go back and forth between the two structures? I mean, if I take if I take this bond and I go and kill the plus charge, I go back to the previous structure, right? So if you look at these blue arrows, it goes back and forth like this, right? Okay. So having electrophile, needless to say, I mean, here's the electrophile, is this one, same thing, right? But it doesn't matter which one I use. I mean, I think it's cleaner if I use this one to do the attack. So, so far I talked about this and everything here, but let me talk about this. So this benzene has a methyl group, which I made it right. So I'm going to ask a few questions. So first of all, is this electron donating or withdrawing? Donating. Does this ever change? No. The second question I'm asking is what kind of activation does it have? It's activating. And in the question mark, I need to put the word ortho or para. Then the answer is, it depends. The answer is, it depends. If it's electrophilic aromatic substitution, which it is, then it is ortho para directing, activating, right? Activating or directing, so the correct word is directing. Directing. It's ortho para directing. Okay? It's orthopara directing and also it's activating. So there's different words, you know. So I mean, I guess the best order is to put them this way. Okay. First, we address the issue. It's electron donating. That would be true for the first page of organic chemistry, the last page of organic chemistry. Then you ask, in order to ask to fill in the rest of them, you have to say what you have. So this is answered without looking here at all. It's electron donating. We have answered this from the very beginning. To answer if it's activating or orthopara directing, you have to see if it's EAS or NAS. Since you know it's electrophilic aromatic substitution, how do you know this? Because you did all of this work, you saw the plus. Then you say it's activating orthopara directing. Okay, now we have all the information. Now we can do the mechanism, right? So here's the mechanism. Okay, we have the CH3 group over here, right? So we have the double bond. Okay, and now we have one of these double bonds that is going to come and attack the electrophile. Now, notice I have the electrophile already there. Okay, so I took this and I copied it over here, and of course, I'm going to do the reaction here. Okay, and as a result is here. Okay, we have these. Now, this can attack. I mean, let's go back to what we said before. We said it's going to be orthopara directing, so I can add it over here, or I can add it over here. Okay, so let's just verbally say it. So you think it can add over here, or this can add over here. Yes? I mean, I'm not going to do it twice because I think we have the question. It says, consider whether an addition or substitution will take place. I mean, between the two, in this case, it will not make a difference. But typically, statistically, the ortho has more possibilities. This is not very bulky. But so let's do a substitution of the para position. As a matter of fact, yesterday it was the same issue answered here for something slightly different, and I showed the Tuesday people on the ortho position. I said do the para position, maybe do the para position. Okay. So let's do the para position, and just gently do this, and so if that's the case, let's adjust it a little bit. And if you do the para position, right, so you will take this and attach it over here. Okay, so if we have this, then the new bond will be over here, and then you're going to have this carbonyl here and then this here. Okay, so now we have a plus charge someplace, right? Okay, so where would you put the plus charge in this case? So you put it over here. Let's put it over here. Okay, and let's have a hydrogen. Don't forget the hydrogens, because the hydrogens can be an issue, right? That means if we forget them. So now let's do some resonance. Now the methyl group will still be there. Let's keep it here. And then we have okay, so what did the plus charge travel? It traveled for the methyl group, yes? All right? And then we have one more, right? Yes, and then we can do this. Right, so the plus charge went from 8 o'clock to 12 o'clock, and again, okay, and the plus charge moved at 4 o'clock, okay? All right, and now let's close the brackets. And now, let me just verbally say this. Obviously, is there more resonance structures? You can do a resonance structure here. You can open this up and make plus and minus, but that's minor structure, right? I mean, here's what we're concerned about. So if we call this A, and we call this B, call them prime, and C prime, can I use the A prime to get the final product? Well, in order to get the final product, I need to abstract this hydrogen right here, yes? So in order to abstract this hydrogen, I need a base. So if you look everywhere here, right